Hey there YouTube, back home, still no name. Last time we asked what happens when a minus sign sneaks into the general equation for an ellipse. The short answer is that it looks something like this. Hyperbolas are kind of like two bowls facing in opposite directions. They can either open up horizontally to the left and right, or vertically up and down. Which one depends on the order of the formulas, because unlike ellipses, the order does matter because of the subtraction sign. Curse subtraction sign, always so negative. In addition to direction and asymptotes, the defining features of the hyperbola include the vertices, which are the turning points of these graphs, and the foci, which are inside the curves like they are for parabolas. All these things are important to know to be able to draw these curves, which is most likely what you'll be asked to do. And all of these features can be found using the general equations. Just as with all the other conic sections, your teacher may write the general equation differently. That's okay, but personally I just like to keep the a squared underneath the x term and the b squared beneath the y term. That just makes it easier for me to remember the next few steps, and it keeps things consistent. On to finding the features. First figure out whether it'll point horizontally or vertically. The easiest way to do this is to find the positive term, that is, the one that doesn't have the minus sign. It could be the first one, but it isn't always. If it's the x term that's positive, then it'll open in the x direction, or sideways. If it's the y, then it'll open in the y direction, or vertically. The next couple steps are simple too. The center is at h, k, just like with the other conic sections. After that, we draw the lines that will become the asymptotes. These lines pass through the point h, k, and their slope comes from these numbers b and a. Oh yes, number a and b. Some of my favorites, right up there with e and I. Anyway, the slope of this positive asymptote is b over a, and the slope of this negative asymptote is negative b over a. More on that later, but on to vertices. If it's a horizontal hyperbola, the vertices are distance of a out from the center to the right and left. If it's a vertical hyperbola, it's a distance of b up and down from the center. Locating the foci is very similar, only instead of adding or subtracting a number a or b, we'd use a new number, c. This number c comes from this formula here, which you'll recognize as the Pythagorean theorem that we know and love. If we simplify this down, we know that c would equal the square root of a squared plus b squared. And you would go out from the center to the right or left for a horizontal hyperbola, and up or down for vertical hyperbola. Example time! Looking at the positive term here, we see that we're working horizontally for this problem. We are centered at -2, +3, which we get from these numbers in the parentheses. For the asymptotes, I know the slopes are b over a and -b over a. We know a is the square root of 16, or 4, and b is the square root of 4, or 2. That means that the slopes are going to be plus or minus 2 over 4, or plus or minus 1/2. To draw this, I'm just going to go over 4 and up 2, over 4 and down 2, back 4 and up 2, and back 4 and down 2. Then I'm going to draw these asymptotes through the corners. Since we're going sideways, we're going to go out to the right and left of the center by distance of a, giving us, to the left, a vertex at -6, 3, and to the right, a vertex at 2, 3. Similarly, to find the foci, we're going to go to the left and right a distance of c, which is the square root of 20, or about 4.5. So we're going to go to the left and to the right, giving us foci as written here. Technically, we should reduce the square root of 20 into the square root of 4 times the square root of 5, which then equals 2 times the square root of 5. Now for the drawing. Just make 2 swoops through the vertices, approaching the diagonal asymptotes. As long as you provide the vertices, foci, center, and asymptotes, a sketch should get you full credit. There's one more thing I should mention. If we were to connect these dots we drew for drawing the asymptotes, you would end up with a box. Just as an ellipse has major and minor axes, hyperbolas have transverse and conjugate axes. The transverse axis is the one that shows you the distance between vertices. If it's horizontal, the transverse axis will be 2a, and the conjugate axis will be 2b. Flip that for vertical hyperbolas. Let's just do one more. Let's write down everything we know from this problem. The center is at 2, -1. Don't get confused by the order, it's still x, y. Speaking of order, the first one, which happens to also be the positive term, is y. So therefore it will be a vertical hyperbola. Everything else has to do with values of a and b. Solving for the square roots, we get a to equal 2 and b to equal 3. That means the asymptotes have slopes of plus or minus 3/2. We can also find c, the focal distance, by taking the square root of 4 plus 9, which is the square root of 13. The transverse axis is the vertical one, making it 2b, and the conjugate axis would be 2a. If you ever get a question about axes, don't even worry about drawing it. Just remember that the transverse axis goes the same direction as a hyperbola, horizontal or vertical. That way you can just look at the equation and do 2 times a for horizontal or 2 times b for vertical. For when you do need to draw it, mark the center. In our case, -2, 1. Draw the asymptotes over 2 and shifted 3 in all directions, and then draw the asymptotes through the corners of this box. The vertices are b above and below the center. And then the foci are a distance of square root of 13, or about 3.6, away from the center also. Draw the curves approaching the asymptotes, and you have a hyperbola. So why do we need to know all this stuff? You probably never heard of a hyperbola before math class, but the funny thing is they're used in all sorts of different things that you would never think are actually related. Similar to parabolas, hyperbolic reflectors reflect radiation, like light, into a fixed point called the focus, making them excellent reflectors for various signals. Speaking of signals, back in World War II, ships would use signals from the lower end system to triangulate where they were, using the math of hyperbolas. On the subject of position, objects in our solar system traveling too fast for orbit often follow a hyperbolic path around the sun that can be plotted using these formulas. Two places you may have seen hyperbolas in your everyday life include the cooling towers of a nuclear reactor, which are actually rotated hyperbolas called hyperboloids. Also, if you turn on your lamp tonight, the cone of light will intersect your flat wall, creating a conic section. Which one? You guessed it, hyperbola. Well, that's the end of conic sections. Does that mean we're done with them? Well, actually, a lot of trig is based off of circles and triangles. To be more specific, the unit circle. And you can find more about that later.